You ever watch a sci-fi movie and think, could that actually be real? Well, today, we're diving deep into one of the all-time classics, Stargate, to see how its incredible tech lines up with some of the most mind-bending ideas in real-world physics. So get ready to dial in. Door to heaven is Stargate. It all started with this one cryptic phrase. These were the words spoken by the brilliant linguist Dr. Daniel Jackson that finally cracked the code on a mysterious, ancient artifact and, well, opened up a whole new universe of possibilities. So picture this, it's 1928. On a Giza plateau in Egypt, archaeologists are digging in the sand and they unearth this thing. A massive ring, bigger than anything they've ever seen, covered in these strange, unknown symbols. For decades, it was a total mystery. So what was it? Some kind of art, a weapon, or was it really a doorway? The answer was hidden right there on the ring, in a code that was, get this, a mind-boggling 10,000 years old. At first, everyone got it completely wrong. They thought the symbols were just words, an ancient language. But then Dr. Daniel Jackson comes along and has this incredible aha moment. He realizes they aren't words, they're pictures of star constellations. They were coordinates, a map to a destination somewhere out there in space. Okay, so with the code cracked, they could finally turn this thing on. But how is it supposed to work? Let's take a look at the fictional instruction manual for this amazing piece of tech. In the movie, it's basically a four-step process. First, you dial the address, locking in the glyphs for your target. Then the gate forms a connection, which it calls a stable wormhole. Step 3 is where the magic happens. You step through that shimmering pool of water, the event horizon, and you're instantly broken down and reassembled at your destination. And finally, the link is terminated. Now, those words, wormhole and event horizon, they weren't just made up for the movie. They come straight from theoretical physics. And that leads us to the really big questions, right? What exactly is a wormhole? And how on earth could two objects, maybe millions of light years apart, be connected in an instant? Well, to even begin to understand that instant connection part, we have to look at one of the weirdest, most fascinating, and frankly coolest concepts in all of physics, quantum entanglement. So, quantum entanglement is this bizarre feature of the quantum world. It's when you have two or more particles that are linked together in a very special way. Their fates are intertwined. It doesn't matter how far apart they are, across the room or across the galaxy, they behave like a single system. And here's where it gets really mind-bending. Let's say you have two entangled particles. If you measure one and find out its spin is up, you instantly, and I mean instantly, know that its partner's spin is down. There's no signal sent, no travel time, it just is. This whole idea was so strange, so completely against everything we thought we knew about the universe, that it really bothered Albert Einstein. He famously called it spooky action at a distance because it just didn't make sense to him. It seemed to break the ultimate speed limit, the speed of light. And for decades, scientists debated it. Einstein and his colleagues wrote a famous paper in 1935, arguing that quantum mechanics had to be missing something. But then, work by physicists like John Bell in the 60s, followed by countless real-world experiments, proved it. This spooky action, it's real. It's a fundamental part of how our universe is put together. Okay, so entanglement gives us a way to think about the instant connection. But what about the tunnel itself, the part you actually travel through? Well, for that, we need to talk about another wild idea, wormholes. A wormhole isn't just a convenient sci-fi plot device. It's a serious theoretical possibility that comes directly from the math of Einstein's own theory of general relativity. Basically, it's a hypothetical shortcut, a tunnel through the very fabric of space-time itself. And this idea has been around for over a century. It was first proposed way back in 1916 and was even formalized by Einstein and his colleague Nathan Rosen. But there was a catch, a big one. The early models showed that these wormholes would be incredibly unstable. They'd basically slam shut before anything, even light, could get through. It wasn't until the late 80s that physicists like Kip Thorne started seriously figuring out how a traversable wormhole might be possible. So it really boils down to two different types. You've got the original Einstein-Rosen bridge, which is a no-go. It collapses instantly. But then you have this theoretical Morris-Thorne wormhole, which you could, in theory, travel through. The catch, to keep its throat open, you need something truly bizarre, something called exotic matter. And that brings us to the ultimate question. Let's put the fiction aside for a second. Could we actually build a Stargate? Let's break down the massive, and I mean massive, hurdles standing between us and reality. There are basically three huge deal breakers. First, you need that exotic matter we just talked about, something with negative energy to prop the wormhole open. We've never seen it or made it in any meaningful amount. Second, stability. Even if you could open one, the act of sending something through it would probably cause it to collapse. And third, the energy. The sheer amount of power needed to create and hold open a wormhole big enough for a person would be absolutely astronomical. We're talking about the energy output of an entire star. So for now, yeah, the Stargate is definitely staying in the realm of science fiction. But what a fantastic way to explore the very edges of what physics says is possible. It really gets you thinking, and it leaves us with one heck of a question. If we ever did figure all this out, if we finally opened that door, where's the first place we should go?